Okay, welcome to my review. Just a second.
I knew I went back here for something. I remember.
Okay, now, while I was gone, I hope you copied all the words off the board. Did you do that?
Yes.
Excellent. Okay, now, what I did was I numbered the terms, and I gave 20 minutes for everybody to do a little bit of a review. Now, the students are going to do the review by feeding me the information. And what I'll do is, I will take some notes in blue, and then I'll erase it. So anything on the board is going to be based on that number. Clear? Does that make complete nonsense? Excellent. All right, so what's number one? Kinetic energy. Feed me some information. Okay? Kinetic energy. 1/2 mv squared. So that's the equation for kinetic energy. Okay, we're doing one. That's the equation for kinetic energy. What does that automatically tell you? That kinetic energy can be dependent upon what two things? This is my quiet class. I feel like I'm in Al Noor Hospital in the brain trauma recovery unit, and we're all trying to learn how to talk again. Okay? Maunus?
Mass and acceleration.
What, excuse me?
Mass and acceleration.
See, Maunus is actually from southern Alabama, but after the stroke, he now sounds like he's from Denmark. It's really quite amazing. Yes, I'm sorry?
I believe it's mass and acceleration.
No, it's mass, close. Mass, it's because it is a motion, it's mass and velocity, or mass and speed. How fast something's going, and its size. It's mass, not its weight, but its mass. What information does that also give you about kinetic theory? We're just going to bounce over here just for a second to number 11. What are some things about kinetic theory that are important? The fact that a particle of gas is actually a particle. It's a ball. It's a round object. And it undergoes collisions. And those collisions are perfectly elastic. Somewhere. Where's elastic? Remember?
14.
14. Elastic. An elastic collision is that you have a collision and there's no net loss of energy. You collide with a molecule, and that you can transfer energy to that molecule, and that molecule will transfer back, but there's no loss of energy. Energy is transmitted throughout the medium, but there's no net loss of energy. That's an elastic collision. If I take a ball, let's say remember the old super balls? Are you too young to know what a super ball is? Well, a super ball was a ball where you could drop it. If I drop a ball from this height, it'll maybe bounce about a third way back up. It loses a tremendous amount of energy. But if I drop a super ball, it'll come up to maybe that height. It's amazing, really. It's almost elastic. Or let's say this. A super ball's bounce is much more elastic than a normal ball's bounce. Okay? Elastic. So now I've connected kinetic energy with kinetic theory, with elastic collisions, with mass and speed. Anything else we want to say about kinetic energy? Let me say this. Can I write in here? This is blue. Okay, can I write right here for a minute? Okay. Work, force times distance. Yes? Kinetic energy equals 1/2 mv squared. Potential energy. Mass times acceleration due to gravity times height. Okay? This is going to be force is mass times acceleration. So force is going to be kilogram meters per second squared, correct? Times distance, which is meters, right? right? So that's going to be kilogram meter squared over second squared. As energy. Clear? So isn't that interesting? And I think I did that on the first day. That if I look at the units of all these three, you're going to get the same thing. So that's force times distance, kilogram meter squared per second squared. Let's look at this one. This is going to be kilograms meters squared over second squared. Same thing. Those are the units for energy, correct? Let's look at this one. MGH. This is going to be kilograms. This is going to be meters per second squared times meters, height. So that's going to be kilograms meters squared over second squared. Remember I did that the very first day, and you kind of looked at me like, what is he doing? The day before vacation. Not only doesn't this make sense, but I refuse to make sense of it. That's what you're doing. I can look right at you. True or false? But all of a sudden it makes a little bit more sense now, doesn't it? Kinetic energy, potential energy, and work. And what are those unit labels? If I, instead of going around and saying that the unit labels are kilogram meter squared per second squared, what do we say? And the word's not up there, but what do we say? It's a person's last name. No, Newton's, no. Professor Joule. Joule, it was his last name. That's why the unit labels we just put are J. So instead of walking around and saying the unit labels for energy are kilogram meter squared per second squared, we just say they're joules. Clear? Yes? Okay. Now, can we push on from kinetic energy? Are you comfortable with that? Let's go on to potential energy, which we've actually already talked about. What are you noticing about the terms on the board?
They're like related.
Go ahead.
They're like related to each other.
Who told you that?
No.
Did I tell you before class to say that? What did he say?
They're related.
Yeah, everything is related. People ask me, what's the hardest thing about teaching chemistry? You know what I tell them? Breaking it into individual concepts and teaching those concepts isolated from one another in a discrete manner is literally impossible. And isn't that what you really want to, isn't that the way you want to learn? And don't teachers teach you that? By actually teaching you in the beginning of a unit vocabulary. Why do they make you memorize words? Why? Memorize the definition of words. Is that a good thing or a bad thing? Maunus, you're extremely intelligent.
It seems like a bad thing.
Seems like a bad thing? Okay, we'll take that for a second. Okay, seems like a bad thing. Memorization, vocabulary, bad thing. Anybody else? Does anybody agree with him?
Yes.
Okay, so this is like a Danish thing. The other Dane in class agrees with them. I like that. Now, were you also from Southern Alabama, but before your stroke? And now you're recovering and you actually think that you're Danish? Excellent. Excellent. Am I being silly? No, I really mean that, no. So, I will say to Maunus, I agree with him and I disagree with him. Why am I spending time on this? Because for you to appreciate what I'm doing, it's important to understand this. Sitting down and memorizing vocabulary words is very important. So I completely disagree with you on that. As long as it's done in the beginning. Because learning doesn't take place in a vacuum. Thank you, Dr. Khan. You know who you are. I had a guy named Dr. Khan. He used to say this all the time for biochemistry in college. Learning doesn't take place in a vacuum. If you don't know anything, you can't think about it. So it starts with definitions, and then what's going to happen after your studying of the material? You're going to make connections among those words, and that's called learning. So if you're learning vocabulary after the study of the unit, that's a little weird. So it's important to start off maybe with a little vocabulary. That's why you actually have a worksheet vocabulary, because it introduces you to the unit. It's not something you do at the end of the unit. But now you're seeing that these individual words that you may not have understood in the beginning of the unit, now you understand the connections, and that's the hard part about teaching chemistry. Making sure the timing of your presentation is correct. So by the end of the unit, it should be hard to number everything, give you individual words, and then have you give me the information back during the filming and go over one word apart from all of the other words. Do you get it? Your inability to do that shows me what? You've learned something. You get it? Okay. So potential energy. What is potential energy? It's energy of potential. I'm going to raise the potential energy of this marker. I'm going to lower it. So just based on that demonstration, what would you imagine potential energy is dependent upon? Yes?
Position, composition.
Position, yeah. Height. If it's height, vertical, right? Height, not just distance, but vertical distance, height. Acceleration due to gravity. It's going to accelerate, right? Yes? So it's going to accelerate a distance that has a mass. So it's going to accelerate. What's mass times acceleration? I had it over here. Oh, here it is. Force times distance. Isn't force mass times acceleration? That was the first thing we learned in this unit. We had to define force. We had to. We could not proceed. What is the study of force and motion and energy called in physics? One word starts with an M, sounds very complicated. It's called what? I teach you how to do a jump shot. I have to teach you the blank of the jump shot. The mechanics of the jump shot. So the study of mechanics in physics is the study of force, motion, and the resultant energies that exist. And that's what you have to learn. The most important equation, one of the most important equations early on in physics is called Newton's second law. Force equals mass times acceleration. Clear? Okay. What's next? Number 3, melting point. What is melting point? Somebody define it for me. Somebody define it for me. Let's see if you can define it using words that are already up here. What is melting point?
It is the point where
The point where
a substance gains enough kinetic energy,
a substance is going to
gain enough energy.
gain or lose what kind of energy?
Kinetic
Kinetic energy?
and potential.
Kinetic energy?
Yeah.
Is there a temperature change when something melts?
Yes.
There is. Something goes from 0 solid to 0 liquid, there's a temperature change? Something melts at 0. Water melts at 0. It goes from solid water at 0 degrees to liquid water at 0 degrees. It melted. Is there a temperature change? Is kinetic energy involved? Absolutely not. But what's involved? Potential energy. And what's that potential energy gained or lost called? It's not up there. Should be. Heat of fusion, right? What's the heat of fusion in water in grams per calorie or kilograms per kilocalorie? You remember? What is it? I can't hear you. 80 kilocalories per kilogram, or 80 calories per grams per calories, right? Sorry, 80 calories per gram. Did I say calories per grams per calories? I meant 80 calories per gram or 80 kilocalories per kilogram. Right? What else can you tell me about the melting point? What else can you tell me about the melting point?
It also depends on the pressure.
It depends on the pressure. I like that. And what diagram helps review the fact that melting point is dependent upon pressure? At very low pressure and low temperature, is there a melting point?
No. No yellow triple point.
No. What's it called? No, at very low. Let's say at 0 degrees Celsius, this is water, 0 degrees Celsius and less than 600 pascals. Less than a kilopascal. Less than 600 kilopascals. Is there a melting point?
No, sublimation.
What is it called?
Sublimation.
Sublimation point, right? Because it goes from a solid to a gas, doesn't it? Yeah? What's the opposite of a sublimation point? I'll give you a hint. It's DP. Think in law. What's the word in law when you give testimony in front of a judge? Like, it's pretrial. I don't know the definition of it. I'm not a lawyer, but let's make up a definition. I may be wrong. Pretrial testimony in front of a judge. What's it called? Jen, you know, and just not talking because you don't feel like paying attention anymore, or am I being unfair? What is it? You don't know, okay. Anybody else? Yes?
Deposition.
Deposition, that's right, deposition. So it's DP, okay? So where are we? Oh, melting point. What else about melting point? Who's looking at melting point? Who's doing the melting point thing? That's a drill in the back. The aliens have landed and they're drilling from the roof down, but our roof is made so well that they'll never get in here. Learning can continue. So if you hear a drill, it's aliens are drilling. They landed on the roof, but they're very little, the aliens. We can take them, okay? We can take them. Okay, anybody else?
It occurs when the disruptive vibrations are strong enough to overcome the internal attraction.
I have no idea what he just said. No, I'm teasing. Yes, that's actually correct. Would you like to say it and I'll repeat it into the camera? You're being very quiet. Just say it. Just say what you just said. It was wonderful.
It occurs when
It occurs when
the disruptive
vibrations of the particles occurs when the disruptive vibrations of the particles are strong enough to overcome the intermolecular attractions among the molecules, such as hydrogen bonding for water, etc. Is that approximately correct? Excellent. And that's correct. We're going to talk about these in a minute. But these are the biggies. This is what makes matter do what it does. Okay, good. Now, number 4, boiling point. Boiling point could take quite a while. I may actually not get through this in one try. It may take me a while to get through this. We're only on number 4 and we've got like 5 minutes left. Okay, so what can you tell me about boiling point? Anybody? Yes? It's when the vapor pressure of the liquid is equal to the atmospheric pressure. Now, does evaporation occur all the time, continually? Yeah, it does. Of course it does. And what's it called when water evaporates below the boiling point? What is that called? It's called evaporation. When liquid goes into the gaseous form less than the boiling point, it's called evaporation, right? And what happens when it goes into a vapor At the boiling point, what's it called? It's not called evaporation, although it is, but we won't tell anybody. But they actually make a distinction. It's called vaporization. I know it's weird. I know. Go figure, right? But anyway, you see the bubble. You know those bubbles in boiling, right? So I have a beaker, and I have a liquid, and I have these bubbles, little tiny bubbles down the bottom. They really want to form, but they can't form because the atmospheric pressure is not just coming from this way; it's all around the bubble. So the bubble may look like this, but the atmospheric pressure is pushing like that, right? Now I'll draw a macro model of this. In other words, I'm going to blow this model way, way up, and it's going to look like this, okay? That's the little tiny microscopic bubble, and the vapor pressure forces are trying to push out, right? And what happens is you get these enormous forces. These enormous, what am I doing? That are preventing, see? These arrows here, if you look at it in the micro scale, they won't overcome it. They can't, they don't win. But when I boil the water, what am I increasing? By heating the water to a high temperature. We call it boiling. I'm adding what?
Vaporization.
I'm adding vapor pressure, but what am I increasing? The amount of, starts with a K, ends with a Y, kinetic energy. So I'm increasing the amount of energy, correct? Right? What's energy? Remember, force times distance? So there's a force in there, isn't there? Isn't there? So when I talk about energy, does it make a little bit more sense now that a bubble will form? Because people say vapor pressure, but what are they forgetting? That you're increasing the kinetic energy, aren't you? And isn't energy mechanical? And what's the definition of mechanical energy? Know this. Know this. The definition of mechanical energy is force times distance. This is force times distance. You get it? So now the vapor pressure is high enough that these force vectors will overcome the atmospheric pressure and the bubble can form. Gives off the vapor. Cool or what? So let's see, what's the approximate vapor pressure on top of Mount Everest? And no one looked at my lectures. Do you know, I want to tell people out here, that I have all my lectures online, and I actually have students that don't look at them. It's amazing to me. You don't even have to read the book if you just look at my lectures. It's about 33 kilopascals. What's atmospheric, regular, normal atmospheric pressure? 101.3. But we now know it's what?
No, the atmospheric pressure is still 101, but it's just that in the standard temperature and pressure is starting to get defined as 100 kilopascals.
Yeah, it's being redefined. I have to look that up to see what that is, but yeah, it's being redefined as 100. We're still using 101.3. Sounds like a radio station in New York. 101.3, coming to you live, brought to you by chemistry. Okay, now, so would the boiling point be higher or lower on top of Mount Everest? Be lower, be a lot lower. You don't have to go to 101.3, you only have to go to 33. Cool. Let's say we're at the bottom of the ocean. We're at the bottom of Mariner's Trench out by the Marianas. It's an actual country, the Marianas, Northern Marianas country. What would the you don't have to tell me what it is, but what would the boiling point be higher or lower than 100 degrees Celsius? Much higher. Much higher. Why? The pressure, the atmospheric, the environmental, the room pressure would be enormous, right? Every 10 meters, it's another atmosphere. Roughly. Remember we went over that? We'll do it more in gas laws. Yeah. If you go 10 meters down in the water, that's about another atmosphere. So 30 feet. So what's Mariner's Trench like?
11 kilometers.
It's more than 10 meters?
I believe it's, yeah.
So it's going to be many. Somebody find out right now. Oh, we got to leave. Okay, so this is part 1 of test review. Stay tuned. I'll try to finish them next period. Okay? We're off.